In the last section, we dealt with arithmetic sequences. And the big thing with an arithmetic sequence is it has a common difference between the terms in the sequence. Now we're going to do geometric sequences. And the key to a geometric sequence is there is a common ratio between one term and the next. For example, in the sequence 5, 10, 20, 40, each term equals the previous term multiplied by 2. So if you took any term and divided it by the previous term, you would get 2. 10 divided by 5 is 2. 20 divided by 10 is 2. 40 divided by 20 is 2. So it has a common ratio. Or put it in recursive style, an equals 2 times an minus 1. Written as a ratio, an over the previous term is 2. We call 2 the common ratio, and we use r. So one of the big differences between geometric is we look at r. In arithmetic, we looked at d. The general form for a geometric sequence is an equals a1 times r to the n minus 1. In the previous example, a4, so 1, 2, 3, 4, the 40, would be 5, because that's where we started, times 2 to the 4 minus 1. So this part is always going to be 1 less than that. And so to the 3, that's 8. 5 times 8 gives us our 40. To find the nth term, let's suppose we were looking at this sequence of numbers, 3, 3 halves, 3 fourths, 3 eighths. So notice in this case, each one is multiplied by a half. 3 times a half, 3 halves, times a half, 3 fourths, times another half, 3 eighths. So our r is 1 half. We started at 3. We want the 10th term. So it's going to be 3 times 1 half to the 9th power. And of course we have to do the exponent before we do the multiply. So 3 times 1 over 512 gives us 3 over 512. If we want to find the general term for a geometric sequence or a geometric progression whose 4th term is 16 and whose 7th term is 128, now in the last section we had 2 equations and 2 unknowns. However, in this case, when we look at a ratio of the two, so a7 and a over 4, so those are the 2 terms. When we do a ratio of them, notice that the a1s will be canceled out, and then all we have left are the exponents for the r's. Notice that they're always 1 less than the n for that term, and so the a1s cancel. R to the 6 divided by r cubed is r cubed. 6 minus 3 is 3. And since a7 was 128 and a4 was 16, 128 over 16 gives us 8. So r cubed equals 8. Cube root both sides, and we have r is 2. Now that I have the 2, I can go back to my a4. It's going to be a1 times 2, again that's my r, to the cubed. Again, that's always 1 less than that. And so 16, that all equals 16, so a1 times 8 equals 16, so this one actually started out at 2 for the first term. We also have an equation for the sum of n terms. And this is the formula that we use for there. So a1 again, and then r to the n minus 1 all over r minus 1. So if we wanted to find the sum of the first 10 terms of 5, 15, 45, 135, note that the ratio here is 3. 15 over 5 is 3, 45 over 15 is 3, and so forth. So that's our ratio. We started at 5, so there's our a1. We want the 10th one, so that will match in this particular case. And so 3 to the 10th power, subtract 1, times 5, all divided by 2, 3 minus 1, and that gives us 147,620. And of course, geometric terms increase much, well, when they're above 1, will increase much faster than arithmetic ones will. Now, there is a special case where instead of just wanting the 10th term or 50th term or whatever, we have what's called an infinite geometric series. In other words, dot, 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 this actually goes on forever, and what we want to know is what is the sum of that geometric series, and as long as r, and notice its absolute value of r, is less than 1, then our sum, notice there's no subscript here, our sum for that series will be a1 over 1 minus r. Now, we can turn around and use that to show that 0.999 in fact equals 1. And when I say 0.999, I mean it's going to go forever. So it's 0.99999 to infinity. Now, I can rewrite 0.999 as 9/10 plus 9 over 100 plus 9 over 1,000 plus dot, dot, dot. Keep going. These I can then substitute or separate so that the first one's 9/10. Well, the next one is just 9/10 times 1/10, and then the next one is 9/10 times 1/10 squared, and so forth. Well, that then says a1 is 9/10, our r is 1/10, and because again, if I took this one and divided by that one, the 9/10 would cancel out, and I'd have 1/10. 1/10 is less than 1, and so if I plug it into the formula, s equals a1 over 1 minus r, that would be 9/10, our a1, 1 minus 1/10, which of course is 9/10. 9/10 divided by 9/10, anything divided by itself is 1. So, let us look at some examples. First off, if a1 is 5 and r is 2, find an. In other words, find the general form given these two pieces of information, and then go ahead and find a6, or the 6th term. Well, again, remember that an equals a1 times r to the n minus 1. So that would become an equals 5 times 2 to the n minus 1. And that would be our general form. I can't combine them any more than that because I've got to do the exponent first before I can do the multiply. Now, so what is a6? Well, a6 will be, again, 5 times the 2 to the 5th power. Again, that exponent always has to be numerically 1 less than the subscript there. Well, this is 5 times 32. 2 to the 5th power is 32, which gives me then that a6 equals 160. And so I have my first problem. All right, in the second one, we have a5 equals 1/8, a8 equals 1 over 64. Find r, a10, and s10. So, similar to the example above, I'm going to first start off with a8 divided by a5. So, that's going to be 1 over 64 divided by 1 over 8. And of course, we can't divide by fractions, so this is going to become 1 over 64 times 8 over 1. We multiply by the reciprocal, and in fact, we get 1 1/8. Now, that has to equal the general form for A8. That's going to be A1 r to the 7th. And for A5, that's going to be A1 r to the 4. So again, that's A8, A1 r to the 7th, and A5, A1 r to the 4th. Of course, the A1s get canceled out, and I'm left with r cubed, 7 minus 4. So, basically, what I've got here is r cubed equals 1/8, which then means that r equals 1/2 when I take the cube root of both sides. So I have found r. Alright, now I still need to find A1, so I can go back here, or let's see, let's do it over here, give myself some room. What do we know is, we know that A5, which was 1/8, 1/8 has to equal A1, which we don't know, times my ratio, 1/2, and since this is the 5th one, this has to be to the 4th power, which basically is going to be A1 over 16. So basically, if I multiply both sides by 16, I will get A1 equals 2. Again, 1/8 equals A1 over 16. So now that I have r here, and I have A1, then I know that my general form, I'm going to go ahead and put it over here, my general form, AN, is going to equal 2 times 1/2 to the n minus 1. Alright, so we can now say A10 will equal 2 times 1/2 to the 9th power. And this will be equal to 1 over 256. Now, unlike the arithmetic ones, I don't actually need to know what A10 is to find out S10. S10 is going to equal A1, which is 2, times 1/2, that's the r to the 10th power minus 1, all over r, which is 1/2 minus 1. So again, I am using the formula that I had here, in which I have, here's my A1, there's my r, here's my r to the 10th, this one and that one have to match. And so basically we're going to end up with this being 2 times, let's see, 1/2 to the 10th power will be 1 over 1024. 1 over 1024 minus 1 will be 1023 over 1024. And then the whole thing will be over, and actually that's a negative, and the whole thing will be over negative 1/2. This kind of pattern will happen all the time. In other words, because it's this minus 1, when this is a fractional amount, It'll be 1 over something like that, minus 1. You'll always end up with this case of just 1 less than there. All right, so 2 divided by a half, the negative signs will cancel. 2 divided by a half will be 4. And so this will lead to S10 equal to 1023 over 256. So here is my A10. Here is my S10. And of course up here was my R. Those were the 3 things I was asked to find. All right, and number 3 here, we have an infinite sum. I know that it's an infinite sum because of what I see right there, dot, dot, dot. 1/3, 1/9, 1/27. So first off, I want to, I know that A1 is 1/3. And then to find R, I can simply do R is going to be equal to 1/9 over 1/3. In other words, I can take anything in the series and then divide it by the one before. So of course this will be 1/9 times 3 over 1. 3 divided by 9 is 1/3. So my R is 1/3. Now this is an infinite series. R is less than 1. So S equals A1 over 1 minus R. So A1 was 1/3. This is going to be 1 minus 1/3. So that's 1/3 over 2/3. S equals 1/2. So a series in which we go 1/3 times 1/3 times 1/3 times 1/3 and so forth to infinity, the sum of all those terms is 1/2. All right, for our last example, we're going to look at showing that a repeating decimal, in this case 545454, is the same as a particular fraction. Now of course we could just use our calculator, do 6 divided by 11 and get the decimal, but we want to show basically using what we used right up here and similar to the example above where we showed 0.999 to infinity equals 1, we're going to show that this equals 6 over 11. So first off, our decimal, we're going to split it up into a series of fractions. Note that I'm adding 2 zeros each time because I'm moving over 2 decimal places each time. And then similar again to what was up above, I have the first term, and then the next one has 54 over 100 times 100, and then the next one after that has 54 over 100 times 1 over 100 squared, and it will continue the pattern. So from those things I am able to say, well, A1 is 54 over 100 and R is 1 over 100. And by the way, as a general rule, as a pattern, however many decimal places repeat. So in this case, 2 repeated. So my ratio was 1 over 100, 2 zeros. If I'd had 3 digits repeat, so let's say it went 544, 544, 544, then I would have had 3 zeros here, 1 over 1,000. However many decimal places I need to go before I start to repeat. So now using my formula, S equals A1, which is 54 over 100, and then 1 minus 1 over 100. Well, that gives me 54 over 100 over 99 over 100. The hundreds will cancel, leaving me with 54 over 99. Now, this is the critical step. After to get to the end point, I need to factor these. And so 54, of course, is 9 times 6. 99 is 9 times 11. Now, if you're like, well, how do I know I'm supposed to factor it like this? Well, remember, I'm trying to get to 6 over 11 in the first place. And so if I think about what numbers are here, what would 54 be divided by 6? Well, that's 9. What would 99 divided by 11 be? Well, that's 9. And now that I have both of those 9s, they, of course, 9 over 9 is just 1. And I'm left with 6 over 11. And so I have shown, and this is the key, I have shown that 0.54 or 5454 to infinity is the same as the fraction 6 over 11. And so there you have section 7.3.